Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to look at the idea of elimination. This is section 2.2 in our books, so let's come to the chalkboard and let's give this a look. Okay, so 2.2 in our text, using the text by Gilbert Strang, the 5th edition. This is the idea of elimination. Here's how it goes. Today we're going to be looking at examples. So here's our first example. We're going to solve, actually all of our problems today will be solved. What are we going to solve? We are going to solve the matrix equation. I'm going to write it this way. How about 1, 2, minus 1, 1 times the vector of x, and I'm going to give it components to start with. Let's use components of x and y. This will look most familiar to us. Equals, how about minus 1/4? Okay, so right here, let's keep in mind what we're going to do today. This is the matrix equation. Okay, but this you could also think of this as the system of equations. Remember, it's the row times the vector. So this is x minus y equals -1. And it's the second row times the column vector, so it's 2x plus 1y equals 4. 2x plus 1y equals 4. Now, here's what we're going to do. We are going to solve this. We're going to solve this, and we're going to keep track of how our solutions change in the matrix form. So, this is the matrix equation. This is its system of equations. Or we could just say a system. And I'm going to abbreviate equation or equations, E, Q, and S. Now, we need some more notation here. I should have given myself some more space. Let's write it this way. Call this my system of equations. This is my system. And this is going to be my first row. So it's going to, this is row 1. Here's row 2. And I'm going to, for notational, because writing row all the time is going to be excessive, and you'll see why, I'm just going to write R1 for row 1, and R2 for row 2, and if I had a third row, I would use R3, and so on. Now, I'm going to write out some things that we've done before, or you've done before, but I want to be very systematic about the way we go at this. So here's what we're going to do. We're going to use row 1. And I'm going to put a coefficient here. I'm going to use row 1 as my guiding row. And what I'm going to do is eliminate x beneath it. And then I'll have this equation only has y. So it'll be a simple solution. Now, when you first learned to do this, what you might have done is you might have said, well, let's take row 1. Let's take row 1. And we're going to multiply that by -2. So if I did that, what I would get is I would get a minus 2x plus 2y equals positive 2. And then you would have written row 2 down beneath it. Let's write it this way. So this is minus 2 row 1. And then I'll just copy row 2 down beneath it. So you would have said that's 2x plus 1y equals 4. And then what you probably would have done is you would put a line underneath that and you would add these up. You would add these up and you would say I have 0x, and you probably wouldn't even write that, plus 3y equals 6. Okay, all of that, we're going to encode all of that operation a little bit different. Because notice this, once we've multiplied row 1 by negative 2 and we've added it to row 2, we have this new equation. And now we can solve for y. So then we would put y back into, you could put it into this row 1, this multiple of row 1, or you could use the original row 1. So what we're going to do is, we might multiply row 1 by a number, but we're going to always copy it down in its original form. So let me show you how we're going to rewrite that process. We're going to write it like this. We're going to write that as, we want to change row 2. We're going to change row 2 by some coefficient times row 1, some coefficient times row 1, and then we're going to add those, or subtract as appropriate. So here's what we're going to do. I'm going to write my instructions as we want to change R2, so this is the row we're working on. That's what we're working. I'm going to change it by multiplying row 1 by negative 2 and writing my result. So all of that, I would recopy my problem. As row 1 would remain unchanged. So I would write this as 1x minus 1y equals minus 1. First row would remain unchanged. My second row then would become this new result. So I would write this then as 0x plus 3y equals 6. And that, I'm going to recopy that. Let's copy that over here as 1x, write it down, 1x minus 1y equals minus 1, and 0x plus 3y equals 6. That is my new system of equations that result from that operation. And let's take a look. Okay. Notice a few things. One is we started in this upper left. Actually, I'm going to come back to that. So this system, this is my system, has the matrix equation of 1, minus 1, 0, 3. We have the vector of x. We have the vector of x with components of x and y. And this is equal to minus 1, 6. Minus 1, 6. This is the matrix equation. That's the matrix equation. Now, here's what we've got. Notice that coming back over here, I started in the upper left-hand corner. I started in the upper left-hand corner of my matrix. And in the second row down here, my goal was 0x below the 1x, okay? This top left position we call the pivot. And as we have bigger systems, that's going to become more and more important. So, we did this one operation, this operation right here. This was our operation. Actually, it's not just an operation, it's that we operate on the rows. Notice that that's what we changed. Our goal is we changed it by the rows, so we'll call these rows. This is our row operation. And look at the result. This result might seem simple at first, but it's going to carry forward into bigger examples. Notice here, that was my goal, the 0 below the 1, the 0 below the 1, the pivot, the 0 below. And notice this form. We call this an upper triangular matrix. And these numbers here that go from the top left to the bottom right, top left to the bottom right of a square matrix, we call that the diagonal. So when we have this form, we call this when the numbers, in this case there's only one, but when the numbers below the diagonal, are 0, or zeros are zeros, the matrix is called upper triangular. I'm running out of space here. It's called upper triangular. Upper triangular. Okay. Not only that, look at what we started with. Here, our matrix equation began as we hoped. X equals B. We did a row operation, and our result was this upper triangular matrix, and we call that capital U. So now, this is the new equation of U. The vector x remains unchanged, but notice that B began as -1,4. B is now -1,6. So it's not B anymore. We call that C. Once we're to this form, that Ux equals C, we can then simply solve by back substitution. Because all we're solving is 3y equals 6. Find that value. So let's write that down. So let's come over here. So once we are to Ux equals C, solve by back substitution. All right, so let's do that. Well, we start down here. You can look at the system, 3 times y equals 6, or you can look at the matrix equation, 3 times y equals 6. So let's do that. So if we have 3y equals 6, well, we know what y is. So y is 2. And we can keep going. Oh, it gets better. And we just substitute. So this implies that if you look here, well, we know y. Y is 2. So then, and 1 times x minus 1 times y, well, y is 2. This has to give me minus 1. Minus 1. So notice that if I multiply this, I get a negative 2. Move it to the other side for a positive 2. Minus 1 plus 2 is going to be 1. X equals 1. And so we can say that the vector x, the solution to our system, is 1, 2. Okay? So that's the basic idea of elimination for 2 by 2. But like you might expect, it applies as we continue on. So we're going to look at a larger system, a system with 3 variables, x, y, and z. So before we do that, I'm going to check my camera to make sure that I'm in the picture. Solve 1, 2, minus 1, 2, 3. Oh, I think I already messed up. I did 4, 9, minus 3, minus 2, minus 3. I think I want a 1 there. A 7 instead. How about that? 7 times the vector of x is 1, 8, 10. Okay, that's the matrix equation. This is A x equals B. Our goal is UX equals C. So let's just note that goal is UX equals C. Now, this is the matrix equation. Let's solve it, though, thinking of it as the system. I'm going to write the system right next to that as we go. So this gives rise to the system of 1x plus 2y minus 1z equals 1. It gives the second row is 4x plus 9y minus 3z equals 8, and minus 2x minus 3y plus 7z equals 10. Now remember our notation, this first row, that's row 1. This second one is row 2. And this third is row 3. Okay. We start up here in this top left corner. And we call that our pivot. The 1. Okay. So we're going to track this as we go. So this is what we need to do. We need 0 x's below 1x. Okay? So there's no confusion here because neither of these are 1x's. So there's our 1x. We need to make a 0x here, and we need to make a 0x here. We're going to do that one step at a time. One step at a time. So here we go. We're going to use that same notation. So if I want to work on row 2, then I write row 2 first. I'm going to say row 2. How can I make row 2? How can I make row 2 using row 1 so as 0x? Well, if I subtract 4 times row 1, then I would have that. And I'm going to call that new result, I'm going to call it row 2 prime. It's still row 2, but we've made a change. So let's do that. Now, we're going to do that very carefully. So what we have is the first row, even though we're going to multiply it by -4, we're not going to write it down, or because we still are going to be working our base from row 1. So let's write that again. I have row 1 is still 1x plus 2y minus a z equals 1. Now, this is where it gets interesting. This says we take row 2 minus 4 row 1s. Well, row 2 is a 4x. We're going to multiply by a -4. That's minus 4x. So then we're going to have a 0x. Then we're going to take a 9y, but that becomes -4 times 2y. So that's going to be 9 minus 8y. That's going to be plus 1y. And then we're going to have a -3 minus 4 times -1. That's a lot of minuses, but that's going to give me -3z plus 4z, 4 plus 1z equals, now this is, I almost fell prey. Be careful, remember we have to continue to the other side too. So this becomes 8 minus 4, 8 minus 4, that's going to be 4. Notice we didn't change row 3 at all, so minus 2x minus 3y plus 7z equals 10. And I'm going to come over here and write that matrix equation as well so we can see what's changing as we go. So that's the matrix equation of 1, 2, minus 1. The row 2 is what changed. We have 0, 1, 1, and then a 4 on the other side. Oops, so we'll get to that. Minus 2, minus 3, 7. The vector x is still x. And then on the other side, we no longer have b. We have 1, 4, 10. We have 1, 4, 10. Now, we haven't gotten to our goal. We need 0 x's below the 1x. We still have that. We're not done. So we can affect that as well. Well, now we're going to work on row 3. And we're going to do that by what? How about plus 2 times row 1. Notice I can't use row 2 because that's a 0. So I always work back, reference my pivot. Sometimes you have to use some fractions, and that's okay, or sometimes you can rearrange the rows before you even start. That's okay as well. But once we start with that pivot, we need to stick with it. So I'm going to use that pivot, multiplying it by 2 to eliminate, to get a 0x in this position, and then we'll record the changes to row 3. We'll call that, it's still row 3, but we've made some changes for row 3 prime. Okay, I'm gonna leave my matrix space here. So I have the new equation, 1x plus 2y minus a z is equal to 1. My second row is 0x plus 1y plus 1z is 4. Now this is where we have this. So minus 2x, but now we're going to take 2 row 1. So minus 2x plus 2 of those, plus 2 x's, that's going to be a 0x. And then 0x. Then we're going to go minus 3y plus 4y, that's going to be 1y, plus 1y. And then we're going to take 7z minus 2z for a 5z. And we're going to take an 8 oh, sorry, 10. So we're going to take a 10 plus 10 plus 8 for an 18. For an 18. Oh, goodness. Wrong row. Shoo! Glad I caught that now. I am sorry. I was looking here. I should have looked here. So this is a 10 plus a 2 for a 12. Let's try that. I think that'll make our lives easier for a 12. Okay. Oh, let's record this. So this is now the matrix of 1, 2, minus 1, 0, 1, 1, 0, 1, 5, times the vector x. Notice it doesn't change. It doesn't change at all. But the right-hand side, b has been changed twice. Now it's 1, 4, 12. It's not c yet. It's some changed vector. Okay, look at what we've done. We have achieved our first goal. Our first goal was to have zeros beneath the pivot. And look at how it looks in the matrix. Here's our pivot. We have zeros below. Now the next thing is, remember our end goal. Our end goal was U, upper triangular. Upper triangular would mean, here's my diagonal. It would mean I'd have zeros in all entries below. All entries below the diagonal. So this one becomes my next pivot, and I want to get 0 in that position. So there's my pivot. And so we want to use the pivot, use pivot, for 0x below. Okay, well, so now we have to change row, we called this as row 3 prime. So we want to change row 3 prime by, let's just subtract, oh, this is our pivot though. Now I'm working here. I'm working from row 2. So if I want to work from row 2 now, so I just need to subtract. So let's just subtract 1 of my row 2 primes. Now, honestly, normally we don't write these primes. We would just write row 3 and row 2, because that's what we're working on. So you could write it like that just for the clarity of the example, but usually you just think of it like that. We're taking whatever our existing row 3 is, we're subtracting our existing row 2. This is where they are at this point. So if we do that, notice row 1 is unchanged. 1x plus 2y minus a z is still 1. What else do we have? We have 0x plus 1y plus a z is 4. And I have a 0. Now look at what we do. We take 0 and subtract 0. That's 0 just as it should be. 1 minus 1 and record the result for 0y. 5 minus 1 is 4, so that's going to be 4z. 12 minus 4, that's 8. That's the new system. And let's look at the equation that it gives. The equation, or the matrix equation is 1, 2, minus 1, 0, 1, 1, 0, 0, 1. And again, look at this. Throughout this whole process, x, y, and z, this is just the scalars. Remember, this is the scalar x times the first column. It's the scalar y times the second column, and z times the third column. So the vector x has remained unchanged. It's still just x, y, z. Only the numbers have changed, not the scalars. But what else has changed is the vector on the right-hand side. It's now 1, 4, 8. Okay. But we've got something else. We have an upper triangular matrix. The reason for this goal is at this point the problem becomes simple to solve. At this level of mathematics, this is as simple as something could possibly get. This is U, the upper triangular matrix, times the vector x, and the result, all the changes to B are now called C. I'll call C. I'm going to pause there for a moment because I need to make sure the camera is in the right place. So back here, camera is in the right place. Once you're to ux equals C, everything that we worked on stays the same. Once we're to ux equals C, we solve UXC. Solve UX equals C with back substitution. Okay, well, what do we do? Look at this. 4z equals 8. You read this. Oh, goodness. Oh, this should be a 4. Oh, goodness. I hopefully saw that you wrote what was correct, not what I wrote 4. But look at what we have now. This is 4z equals 8. This is 4z equals 8. So we have 4z equals 8. What do we get? So z, well, that's 2. Now that we know z, we can solve the second row because only one variable remains. So then what do we get? Then we have 1y plus 1z. This is 1y, because we have 0 x's. We have 1y plus 1z. So plus 1 times z, but z is 2. And that has to equal 4. 4. Oh, well, that's easy. So y is 2. Oh, and our last one says then that 1x plus 2 times y, so plus 2 times y, well, y is 2. Minus 1 times z, z is also 2. Has to equal minus 1. This is a 4, subtract 2, so that's just a 2. 4. Yeah, there, sorry. 4 minus 2 is 2. Move it over to the other side. Did I write that wrong? Oh, this should be a 1. Goodness gracious. Plus 1. Okay, that makes sense. 4 minus 2 is 2. That becomes a minus 2 on the other side. And so what can we say? We can say that lowercase, the scalar x, is 1. And there we have it. The vector x is x, y, z. It's 1, 2, 2. Now, at this point, I need to show you two simple examples that will come up, and we need to be aware of how the math expresses these oddities. So we're going to come over here. I'm going to erase the board and move the camera. Okay, here we go. We have two less examples. here they are. First one is this. We're going to solve the matrix equation of, how about 1 minus 1, 2 minus 2, 2 minus 2, x is equal to, let's try minus 1 and 4. Yeah, 4 should work. Oh, how about 6? Let's just try something large like 6. Something big. Okay, so that's the matrix equation. That's the matrix equation. I'm going to solve it from the system. Look at this. This is the system of x minus y equals minus 1 and 2x minus 2y equals 6. All right, well, let's use our notation. Well, what we would say is this is our pivot. So I'll put a 1 in here. We don't write it all the time, but let's put a 1 in there. So here's my pivot. And I want to get a 0x below. So below pivot. And how are we going to do that? So we're working on row 2, so I'm going to say row 2. And then we do all of our work on row 1. Let's do all of our work here on row 1. How about, let's subtract off 2 row 1s. Well, that's going to give me 1x minus y equals minus 1. 2x, now I'm multiplying row 1 by minus 2. So 2x minus 2x, that's a 0x, that's what we were hoping for. Minus 2y, this becomes a plus 2y, that's a plus 2y equals 6 plus 2 more. 6 plus 2 more is 8. 8, oh my, that did get big, didn't it? 8. Well, oops, gee whiz. This was 0x this became minus 2y plus 2y. Oh, that was a 0y. Well, wait a minute. Well, we've already had the 0x. How do we solve 0y is 8? Well, the answer is that no matter how clever you might be, 0 times anything is 0. So this has no solution. So when you end up with a statement that doesn't make sense or can never make sense, all of a sudden you might feel that your math has failed you. No, what it is that's the way the mathematics explains to you that it just doesn't make sense. Because remember, a solution represents an intersection of some kind. So graphically, what was happening? Let's graph this. Make a quick sketch. Well, I don't know if I should have used 6, but if I let x be 0, then y is 1. So let's put there. If I let y be 1, be 0, then x is minus 1. Oh, look at what we get. So this first line, you go from is this line. And then, let's try this again for the second line. The second line says that if x is 0, y is negative 3. So I'm going to put that, my scale won't be quite perfect. So x is negative 3. X is negative 3, I'll put a dot there. And then if y, we did that. If y is 0, oh goodness. If x is 0, y is negative 3. And if y is 0, x is 3. Oh, okay, that makes more sense then. So if I had done this right, oops. If I had done this right, I think my lines are a little off, but what do I have? I have this. I have no solution. What this means is we have parallel, in this case, lines, but they could be planes. So this is parallel parallel lines. And when there's parallel lines, when there's no solution, it means it's because they do not intersect. Okay? Parallel lines do not intersect. And that is the way the math expresses no intersection. So we have one more of these. Let's try one more. And let's change that problem ever so slightly. How about 1 minus 1, 2 minus 2, times the vector of x is equal to, how about minus 1 minus 2? All right. Let's go through the same process. We'll work with, oh, I should have written this. Let me come back. Let's come back here. I want to write that matrix equation. Let's do that first. So notice that matrix equation was 1 minus 1, 0, 0, times the vector of x is equal to, what did we end up with? Minus 1, 8. So that's interesting. What this says is when you have a row of zeros equaling a number, no solution. When a row of numbers equals, when a row of zeros, row of zeros equals a number, no solution. That's what we get. And that is a funny looking S. We have no solution. All right, let's try one more. Let me check my camera here. So, last example will be this. Example. How about this? 1 minus 1, 2 minus 2, times, we have some vector of scalars x equals minus 1 minus 2. Okay, so let's write our system. This is the system of x, 1x minus a y equals minus 1. It's also the system of 2x minus 2y equals minus 2. Okay, our pivot is this, the one in the top left of the matrix, or the 1x in our system of equations. And so let's use the operation. The operation will be row 2 minus 2 row 1s. Okay, that's going to give me a 1x. Remember, row 1, we just copy it we're multiplying it by 2 to get our new row 2, but remains unchanged. Minus a y is minus 1. And then I'm going to get 2x minus 2x, that's 0x. Minus 2y plus 2y is plus 0y. Equals minus 2 plus 2, that's 0. Oh, well, let's come over here. This is the matrix 1 minus 1, 0, 0, times the vector x equals minus 1, 0. Now, this says that we have to solve by back substitution, and the question is what is 0y equals 0? Well, the answer is that y can be any single number. This will always be true. You can't pick the wrong number. And look at how it's expressed in the form of the matrix equation. It's 0 row equals another 0 row. That is the solution for it. Here we have an infinite number. Infinite number of solutions. Okay. So that is the idea of elimination. Thanks for watching. In our next video, we're going to find out how we do this using matrices. Thank you.